We now turn our attention to something more philosophical, and we'll look over these particular topics in the next set of videos. First, we'll look at the physical meaning of the Navier-Stokes equations through micro, meso, and macro scales. We'll look at Newtonian dynamics, and then Hilbert's problem, and meso to macroscopic scales in Navier-Stokes, and the contemporary status of this philosophical field. First, we have to recognize that from a Newtonian point of view, there's many collisions in the fluid. And we'll look at these in terms of passages from the microscopic to the macroscopic scale. So Newton's laws applied to the macroscopic scale might be seen as an application of Navier-Stokes equations in terms of momentum. Ludwig-Boltzmann might be seen as an intermediate scale or view with the Boltzmann equations. Here's a history slide on him that you can review. A particular mathematical description of a fluid is obviously an intricate process to create, and it's going to be dependent on the choice of scale that one wants to model or predict. At the microscopic level, one will usually see molecules and atoms, particles, and the gas could be described through at least the classical point of view of mechanics via Newton's ordinary differential equations, or a set of ordinary differential equations that tracks each particular particle. In the macroscopic sense, we might be looking for statistics at the end of the day, or through deformation of Euclidean spaces previously described, through averaging behavior for the partial differential equations, which the most popular and well-known is the Navier-Stokes equations. Between the microscopic and macroscopic scales, we might look at the intermediate region, and we'll call this the mesoscopic scale, and this is typically viewed as the one being modeled by the Boltzmann partial differential equation, which we can of course use to derive Navier-Stokes too through moments of the equations. We just want to explain and understand these different descriptions of ordinary differential equations versus partial differential equations, their impact on reversible versus irreversible dynamics, and how it can be related to one or the other from a particular view in mathematics. These questions go back to the great mathematician Hilbert, who attempted to justify the passage from one scale to the other by some sort of limiting or asymptotic type of processes. He tried to show these limitations in these approaches, and in the end it still prevented solving the full problems or finding closed-form solutions using any of the three philosophical approaches. This also might justify this nonlinear behavior of fluid mechanics, that no matter the approach we choose, we will find nonlinear behavior. Even from the microscopic ordinary differential equations, we will see emergence of this behavior, even with particles of mass which is not changing, which might imply a linear system, but it doesn't. Here's a history slide on Isaac Newton, which I'll show here for a second. And in relation to this work, we're most interested in his calculations of speed of sound, momentum, corpuscular theory of fluid mechanics, which came about again in hypersonics a little bit, and many other accomplishments. From Sir Isaac Newton's point of view, the microscopic point of view, a gas is made of a very, very large number of particles that evolve and interact in some dimensional space of 2 or greater. We'll consider 3 to be the normal case, but it could be 2 or 4 or 11. And we'll denote n as the number of particles, which will be very large, and will be much, much, much larger than Avogadro's number, much larger. One simplifying assumption to start would be that of the space domain, and the types of particles which reside in with that domain omega, and how those particles interact. Here we're going to list these most simple assumptions defined at the most basic models. First, the particles are all identical, and they'll be spherical and have mass of unity, and the diameters will be very small, but positive scalar epsilon, which will be greater than 0. The particles will evolve in a periodic box, and the periodic box will let size be unity also, and we'll denote that box by mass script t to the d, which is the dimension, and each side will be from 0 to 1 in the dimension. The particles will interact elastically at each particular binary collision, and there'd be no other type of interactions or forcing to simplify the model. We'll label by integers I in the set 1 to n each per particle, where n is the maximum number of particles. And each particle will be indistinguishable and exactly like every other particle. Within this box and these particles, we'll have xi, vi, which will be the domain td, rd, the position and velocity of the particles for I to n. So we are tracking position and velocity, and we would like, if we knew the position and velocity of all particles, to know the complete future. It's a deterministic system, Laplace's demon. Due to this fact that the particles are going to be spheres and non-overlapping, obviously their distance between each other should always be greater than the difference with epsilon. That's the diameter, recall. We'll denote another number, Zn, which will be a set of configurations of these particles, which will depend of xi, vi. You can think of that as a solution vector, unique in space, and dependent on its space and velocity for every particle. It's unique. There should be an infinite number of solutions. We'll denote in the following by xn the set of positions and vn the set of velocities of the particular particles. These are the sets of positions and velocities which could make up cap z sub n. The positions and velocities of the system of particles obey Isaac Newton's laws, which are the following equations. That for the number of particles, integer I will have their change in position will go as velocity, and of course dvi dt of all the particles will be 0. Provided that the exclusion condition is satisfied, that means they're non-overlapping, the exclusion condition for all j of not I, because obviously a particle will reside within itself, therefore the flow will be in this particular domain and conditions. Just all the conditions written as this set. We also have to prescribe a reflection of the boundaries within this set. For example, if there's no I not equal to j, then the incoming velocities coming in and out for two particles, I and j, are going to be related to the outgoing velocities through the following relations according to Isaac Newton's laws. This is defined as the unit vector, of course, between them. All the incoming velocities will be defined by the fact that the dot product of Vij with the difference of in and out will be less than 0. This means that the incoming velocities are so-called pre-collisional, and we can also write equation 168 in a similar way. This is informs, by definition, a Hamilton system, and in phase B's space is preserved by the flow. The momentum and energy are obviously conserved through the collisions. Here's our momentum equation, and here is our energy equation. Note that it only involves velocities because all the masses are unity in one, so they can of course be canceled out through the systems, they're constants.